All right, so welcome everyone. Today we're very happy to have Jem Albert from Princeton. He's going to talk about imprints of asymptotic freedom on confining strings.
All right, thank you very much. Thank you all for coming. It's a pleasure to be here in Chicago. It's my first time, so thanks for the invitation. And yeah, so I'm going to be telling you about this work, which has not appeared yet, but I've been very optimistic. It should be coming out next week if everything was according to plan. And it's with my fantastic collaborator, Alexandra Holmrich, who is at Caltech. Okay. And yeah, so what we've been doing is trying to see what asymptotic freedom can teach us for confining strings. So I'll go a bit through the logic and so on. But first I'll start by, I'll write an outline, so that you know what to expect, and then can complain if I don't make it. Good, so first I'll discuss string observables. Then I'll do UV input, which will be what we can do with asymptotic freedom, and then we'll see what imprints this UV input leaves on the string, and we'll do this we'll see this in two aspects. So first will be on the string spectrum. And then we'll do on the worldsheet dynamics. Guess I can do this. Okay, so sorry, I was supposed to write this before, but I didn't get to the seminar room before we got here. Good, so let me start by some motivation, which I didn't include in the outline, but always be there, which is what are we talking about? So we're talking about the theory of strong interactions. And this has been known to be like the one of our real world, to be QCD. This has been known for over 50 years now. So I'll just write QCD Lagrangian so we all know what I'm talking about. 1/2 G squared. So we have the Yang-Mills part we were just discussing at lunch, and I'll assume is well defined and so on. And then we can have some quarks, Q bar Q, and we can have some mass. Okay, so we know very well that this is a theory of strong interactions, and it has some quarks and gluons, but this theory is a confining theory at low temperatures. So the objects that we see are not these quarks and these gluons, but they're actually composites thereof, right? So just to sketch, we have the mesons, we have baryons, that will be some collection of 3 quarks, and then they're connected somehow through gluons. And then we have also blue balls, which I'll denote by these loops of gluons and so on. Okay, so these are very non-perturbative objects that come out of this, and we'd like to understand their spectrum and so on. So even though we know what the UV theory is, we don't know, its asymptotic degrees of freedoms are not the ones in terms of which the Lagrangian is written, so we want to understand these objects. Now, it has been apparent since the early work of Tooth that a way where this picture could be, a way to learn about this spectrum would be by recasting this theory, not in terms of a gauge theory, but rather in terms of a string theory, which is where this name comes in, this theory of confining strings. Okay, so this is most apparent in the large N limit when you go to infinity, and then you just look at your diagrams and they arrange into something that looks and smells like a string theory. And then these objects are interpreted as open strings, the mesons. These globals are interpreted as closed strings, and then the baryons, in the extent n to infinity, there's many, many of them, and they become very heavy. They could be thought of, they become infinitely heavy, so they can be thought of as some sort of brains, but not much is known. But the important thing is that things decouple at large n, and then you can study them separately. Okay, so I won't be talking about baryons in this talk. There's a lot of interesting stuff happening there, but we'll just be content with these guys. And in fact, we'll take one more simplification, which is to send the quark mass to infinity. So we'll be doing pure Yang-Mills, but we'll still talk about probe quarks. So in pure Yang-Mills, you just have these objects, the globals are the asymptotic objects that you have, but you can still consider some very heavy quark and anti-quark that are things that are probes for your theory. So you put them there, and they're basically, they extend in time, and they become Wilson lines. So this would be Wilson line, anti-Wilson line. Yeah. So these are probes that you can put on your theory, probe quarks, and this will still create some strings stretching between them, confining string, and you can still study the spectrum of open strings in this theory. By the way, stop me at any time if you have questions and so on.
So the idea of pushing the master infinity is because
it's a simplification. So we wanted to talk about pure Young Mills, and then
just pure Young.
Yeah, just pure Young Mills. Yeah, this was a way to get there. But yeah, we're just doing pure Young Mills where the confinement is well defined and so on. Yeah. But I want to emphasize that there are these probes that it's not just about closed strings. You can still consider open strings between these probes. Okay. Good. So let's see. So now these are all pictures. What one would like to eventually do is to find a string description for pure Young Mills. So find like the QCD string or the pure Young Mills string. So the question would be something like this: what is the worldsheet action? So some integral to the worldsheet of this string. What do I put here so that by the time I quantize the string, the open and the closed string, I'll find the global spectrum of this pure Young Mills. And we don't know. This program of rephrasing gauge theories in terms of string theories has succeeded in various contexts, particularly using ADS-CFT. But for pure Young Mills in 3 and 4 dimensions, there will be everything I'll discuss will be for 3 and 4 dimensions. We don't know what this worldsheet theory should be. Okay. So the question is, how can we make progress? Now, people have made progress by looking at a particular limit of this putative worldsheet theory, in particular at low energies. So the idea is that, well, even if I don't know what the full theory is, I can start building my way up from low energies. So you start with the low energy limit, and this low energy limit is obtained by considering a very long string. So what they do, this is still just review, you compactify one direction of your space. So you consider r d minus 1 times s1 with some radius r, which is this radius here. And now I consider a closed string that winds around the thermal, this compactified direction. Okay. And now I have something, my spacetime is holding my string at some radius r. So I can study a very long string by taking r to be quite large and focusing on this string. Now, what this forces is that the string that I'm looking at is not the global. The global would be some dynamical string that's like a contractible string that's there with some size that's dynamical, but rather this is this other object, which is a long confining string, of which the radius, at least I force like that I force to be very long. Okay. And now around this background, I can study this action. On this, when the string is very long, then I will be able to discuss the dynamics of this string in terms of a low energy effective field theory.
What is long measured? Reference to it.
Yeah, so in this case, I mean, you could think of it in terms of lambda QCD. So it's long, that's the scale of the lambda Young Mills, if you like. But ultimately, it will be the string length. So in the lattice, you'll start by looking at a very long string, and you'll see that it has the energy equal to proportional to the string tension. So to some tension that you can measure, and then it's long compared to this scale. Okay. There's just that one scale. And ultimately, this is related to lambda QCD. So it's up to you whether you fix it in the UV or from this. Good. So, okay. So what does that action look like at low energies? That's very constrained just from symmetries. It's the usual story. You look at the symmetries that you have, and then you write down what you can do. And
are you interpret this S1 as temperature or not?
I'll play with it. So it's all Euclidean. I'll be always in Euclidean, and then we'll play with it. Yeah, we'll just sometimes take time to be here and sometimes take time to be there. So you can do both. You can do it up to you. Yeah. More questions? Thank you. Okay. So what is the idea? So the idea is that now I consider my string. It extends in time, so it has some worldsheet, and then having my worldsheet there breaks spontaneously point-carrying invariance of the background. So it breaks d-2 directions. The directions transverse to the string. So that means that I have d-2 Goldstone bosons xi, which are, so these are the usual, like when we do string theory, the embedding coordinates of the string in spacetime, and then the transverse directions are the Goldstone bosons of spontaneously breaking, like the string spontaneously breaks. So now all I have to do is write down an action that's called like the effective string action or long string effective field theory, which is the following. So you just write the various curvature invariants that are compatible with Poincare invariants of the bulk theory. Okay. So you start, and the simplest one you all know is the Nambu-Goto action. So it just starts with Nambu-Goto. Here you have the string tension, 1 over L squared. That's what sets the scale of this theory. And then you have minus determinant of dx. And then you may have more things about this. Okay, so you're starting just with saying that the action of the string is proportional to its area. But then we are not in critical dimension, right? We're in some D that could be 3 or 4. So you know that this is not a valid theory. So you just interpret this as the low energy limit of the, so it's the first term in an EFT. So it continues with an infinite number of them. And the next one is just various curvature invariants we can have. The next one in particular is the extrinsic curvature to the fourth with some particular contractions of the various indices. And it comes with some Wilson coefficient. This one's called gamma 3. That's the convention, which you don't know. Okay, and then it continues on with a bunch of other curvature invariants with other Wilson coefficients that parameterize basically parameterize the unknown. We don't know this action, so this Wilson coefficient parameterize the tail of the low energy limit. Okay. So good. Now, yeah, is that a question somewhere? Good. So this is the low energy action, and so far we just have we've only used the symmetries of the theory, and we don't know we don't actually know any dynamical knowledge, right? This gamma coefficients are not known from like the EFT pictures. So what you need to do is you go and need to measure them in some experiment. Oh yes, please.
So what's the cutoff for this for the low energy action?
Yeah, the cutoff is where you would have additional degrees of freedom. So here we're only using Goldstones, and then it might be so it basically when you're doing EFT, you like the cutoff in terms of this scale. And now what you do is you start doing loops that are suppressed by this scale. So you have these are higher and higher derivatives. So this square of x to the power 4 and so on. And then the various loops are suppressed. Like each of these guys comes suppressed with extra powers of this mass. That's the large mass. And you can ask, where will it do this break down? So all I'm telling you is that as soon as you start increasing your momentum with respect to this mass, you need to start including more and more loops, the usual story. But then it might actually like really break when you have additional degrees of freedom with these Goldstones. Now this cannot be seen just from symmetries, but in D equals 3 by comparing to lattice simulations that in D equals 4, sorry, by comparing in lattice simulations that I'll briefly mention in a second, it has been seen that there's an additional particle that they call the axion, that is the worldsheet axion, which is some particle that has some mass in it's order 1 in LS. So it actually breaks down pretty quickly, and this EFT, and you need to introduce additional guys that come things like don't quote me on into this, some curvature invariant times 5 and so on and so forth, some particular things like squared. Okay. And then like you include that guy, and then it works very well. But you see, like you're building your way up. So we don't know exactly what we've integrated out to the length here. So we don't know exactly where it's going to break down, at least a priori. Okay. I'll raise this because I'm being
the way you said I wanted to ask a question about it.
Oh, sorry. Okay.
But maybe that's not fair. My question was to what extent it makes sense to include that worldsheet axion in the sense that the bulk theory is gapped, but the gap of the bulk theory is comparable to the cutoff of this string scale cutoff, right? So I would have thought that as soon as you start including additional degrees of freedom, as long as if they're coming in at the same scale as the bulk massive degrees of freedom, then it doesn't really make sense to think of this string in isolation anymore. It's just there's just a kind of defect composite system coupled to the ambient QFT.
So I agree, but we have this guy to play with. So what you're describing from this picture would be, so I have my string and some little glue ball, and these guys can, so if you're at finite n, so you can consider this process where the string pinches off, and then it emits a little closed string shooting off. Okay, and this would be the interaction between something in space time, my glue ball, with the long string. But you see, like just from two-floor counting, this thing is suppressed by 1 over NC. So at finite n, I completely agree with you that you cannot really distinguish one and the other and think of that as an in isolation. You can still discuss it as an EFT, but then you'll need to add additional terms like where a glue ball interacts with a bunch of, so yeah, something like this. But at large n, the point is that this guy should come with a 1 over NC, so we can actually consider the string in isolation. And then it doesn't really matter. Like, yeah, they're just completely decoupled. They just answer the spectrum of this guy times the spectrum of that, and interaction goes.
Yeah, I'm still confused about that answer. So there's no NC in the string tension or in gamma 3.
Correct. Yeah.
So doesn't your X become strongly coupled at the scale where you start to see these other axions?
Yeah, that's so.
Even without the
Sorry, but
even
about NC. So you're happy with treating it in isolation, or that's the confusion?
I think it's the question.
Yeah.
I'm happy with dropping the term you dropped, but so there's no separation of scale between your strong coupling scale and your scale of new physics.
That's right.
And the large NC doesn't seem to help because it's just strongly coupled.
Yeah, so let me restore that guy and I'll put it in quotes. It's not the right guy, but I'm pretty sure this is not the right variant, but anyway. Yeah. So there's this thing which is new physics on the worldsheet, and there's this thing which is physics in the bulk. Physics in the bulk is suppressed by 1 over NC. This guy is not suppressed by 1 over NC. And then yes, this guy fails just using Goldstone fails miserably pretty soon if I don't include this guy. Because this is happening at the scale of my cutoff roughly. So like pretty soon, like when you take energies large enough, you need this guy very easily.
I don't really see how it can help the EFT in the sense that it makes a difference only in the regime where the EFT is strongly coupled.
No, I mean it's still.
Why do you ignore all the other modes and keep only the axiom?
You mean ignore the Goldstone?
No,
no,
there should imagine it's a tower of
No.
things
So
above the
there's a
axis.
single one. As long as there's a single one, and then there's a gap before the next one. Why do you see that? I mean, it's experimentalist way. You have some data that comes from the lattice, and you try to make fits. You make fits with X's, and they fail miserably. You add this guy with some particular coupling, you can fit it, and then you add this guy plus a mass term for this guy, and then you fit the coupling here. I'll call it, I don't know, regime. And you fit this guy with the first plot, and then you check 1,000 different, well, maybe not 1,000, but 10 different plots, and they work very well with those two parameters, even to higher energy. So that means that wherever is the next guy, like some 5 prime, there is a gap over there. And in fact, there's claimed, not by me, that there's nothing else all the way to the UV. Not going to comment on that. But the statement is that this doesn't come with a full tower, and it can be interpreted from the fact that there's 2 transverse in 4. This is in 4D. In 4D, there's 2 transverse directions. Then you can make some arguments with like fields in the UV to say that this should be there. But I really don't want to stop on this point because it's not
Can you at least say why it's an axion?
Yeah, because this object that I failed to write here makes it such that this guy is parity odd. So that's why the quotation mark. And it's like something like
R wedge R.
Yeah, R wedge R. Yeah, that's basically it. Yeah. Ish.
Something like that.
Yeah. So, yeah, I clearly should have prepared better. But I will not be talking about the axiom.
So that R is the R of the worldsheet metric or the R of the pullback metric
It's
from the ambient scale?
yeah, actually I think it's K wedge K. I think it's this.
Yeah, that makes
K
sense.
wedge K. Yeah. I think it's that. It's an extrinsic curvature.
Extrinsic curvature, okay.
This is work by the way, I'm not giving you references because this is a Blackboard talk. But yeah, this is work by the Boston of Venko and collaborators. And then they have, but this term was actually written earlier on, I think by Polyakov. But then now it's understood that it's actually there. And when you compare to, like now we have that lattice data and they compare it and they can actually even measure the coefficient in front here. I think this one's better. More questions? No? Great. So, okay, so let me recap a bit. So we have this action that at very low energies, I'll get this guy if you like. Have these coefficients, and I was going to discuss how these coefficients how these coefficients are measured, and they're measured by looking at various observables. So you need to look at observables of the string, try to measure them, and extract it. So the main observable that people look at is the ground state energy. Ground state energy. and it's this thing. So they look at that string over there, long string, and radius r, and then they can measure it in the lattice as a function of r. And it looks something like this, where at large this is r. So at large r compared to that string length, you have that it's linear, and this energy is proportional to 1 over Ls squared times r. But then it eventually starts deviating from this linear behavior, and it goes down. It goes down with some corrections that are parameterized by these Wilson coefficients. Okay, so by making these are points that they can get in the lattice, then you write your action in terms of Wilson coefficients, you compute the ground state energy, and you make a fit. And then from that you can extract gamma 3, the next one is called gamma 5, and so on. And even you could get the mass of the axion and so on. That's exactly how they do it. Oh, in that case, they don't just look at the energy of the ground state, they also look at the energy of the excited state. Okay. So by looking at the energy levels that you can measure from the lattice, you can fit these various coefficients at low energy to this region over here. But then soon enough, as you go in, this
what is the R when this starts to happen?
In units of LS.
Yeah.
Yeah, I mean it's just order 1 in units of LS. Like
but that's where you're getting loose of your EFT control, right?
That's right.
Yes,
Yeah,
is the cutoff.
That's right. So it's quite tricky, and in fact, it breaks down pretty soon. Yeah.
And then how do you fit the full EFT? I mean, still using EFT to do a fit, but there are some arbitrary number of higher order options.
Right. So I mean, yeah. So the better way so when they're doing it's fair criticism, and in fact, what you do is you start doing more and more coefficients, you start fixing more. But now what they're using is the excited states, and then you have more data at the same region. And then from that, you can more reliably obtain these coefficients. I'm afraid I don't know. Yeah. Well, I mean, yeah, it's basically that. Yeah, you cannot trust it all the way down, and then this fits like have some error bars, and you can only measure like best the lower ones. As soon as you start going higher and higher, you need to go down lower and lower, but then that's when it fails more. So
but also the splitting between the ground state and the excited states would be controlled by the Wilson coefficients, even at large R, right?
This separation, yeah, that's right. Yeah.
Even at large R.
That's right. Yeah. And that's why you'll very quickly see that there's some guys that behave in some way, some guys that behave in the other, and those depend on whether you have an axion or not, and that's what hinted to the existence of. Okay. So this is one observable that is controlled by this guy, only a large R in units of the string length. Another one is the S matrix. So what do I mean by the S matrix? This is the S matrix on the 2D theory. So I consider a very long string, and I put a ripple here and a ripple there, which is some xi transverse direction, xj, and I shoot them in with some momentum p. And then they come in, they interact, and then they go out, potentially in some other xk, xl. Okay, so this is the simplest, the 2 to 2 S matrix. This is S of S, Mandel's invariant. And this is some process that describes the dynamics of my worldsheet theory. I'm not talking about space-time at all. I'm at large n. I just have this Goldstones interacting. And at very low energy, so when S is much smaller than 1 over Ls squared, then again, it's described by these Wilson coefficients. And you can compute the S matrix in terms of this Wilson coefficient. And then it has been used relatively recently by people in the bootstrap community, in particular, João Penedones, Pedro Vieira, and collaborators, where you say, okay, so I have a full S matrix that would be obtained from whatever theory this is, and this must satisfy the very basic principles of unitarity, crossing, analyticity, and so on. So if you plot singularities in the complex S plane, you will have an S channel cut over here, a T channel cut over there, and it'll be analytic in the upper half plane. Now you use the fact, so here the statement is that down here, or close to the origin, you can use effective string theory. So this radius is in units of Ls, and then when S is very small, around here you can use an expansion in terms of this Wilson coefficient. But then beyond that, we don't know, but you impose the fact that it has to be like satisfy causality, and therefore it should be analytic. And here you use unitarity, the fact that S should be bounded. Okay, and then with these principles and some tricks about complex functions, you can obtain various bounds on these coefficients. Gamma 3 has to be bigger than some number that you can obtain. Okay, so these are two approaches to obtaining these coefficients. One is by actually measuring them in lattice in lattice simulations. The other one is to obtain bounds from bootstrap on the string. Okay, but what I want to emphasize is that this whole description is only about the low energies of the string, and it applies to any theory of strings. So not just in confining strings, it also would apply to vortex lines in, say, the Billion Higgs model or some type 2 superconductor, and it also would apply to cosmic strings and so on. So any theory that you have long effective strings can be written with an action in terms of curvature invariance, and it's just that these coefficients here, this gamma 3 and so on, will be different. Okay, it will parameterize the theory that they came from. And in particular, these bootstrap bounds will also apply, because we only use the fact that it has to be a consistent theory on the worldsheet. Okay, so it really, from this perspective, it forgot what theory this string came from, and that's what with Alexandre wanted to do, which was try to input into the string worldsheet the fact that we're interested in pure Yang-Mills in this theory over here. Okay, so the question was,
what the existence of the string itself kind of part of that? I mean, we have the fact that we have a defined string whose energy is linearly proportional to its length.
That's right, but I want to learn something about this string that wouldn't be satisfied, for example, from in the Billion Higgs model, something like that. So I'll be more specific in a second. So the main point that we're going to use, is the fact that this theory is asymptotically free at high energy. So if I consider high energy processes, I can use the gauge coupling here, this one here is small, and then I can use perturbation theory to compute things in the UV. Okay? So the question is, can I use asymptotic freedom to learn something that I didn't know about the confining string? And this is a difficult question because what this means is that you need to find some observable of the worldsheet that in some regime, and of course it'll have to be some high energy regime, but in some high energy regime can be computed perturbatively with this Lagrangian over here. Okay?
Why should you still have the string?
That's a very good question, and indeed you don't always have it, but there's one setting where you still do. So I'll start by discussing where you no longer have the string, and then I'll discuss where you still do. So why is it difficult? Well, you could try these two observables, right? So I told you about the ground state energy, and I told you about this matrix. Now you can ask, of course, I mean, UV freedom, like asymptotic freedom will kick in at high energy. So can you ask, like, what's the high energy behavior of this guy and that guy, and is it controlled by asymptotic freedom? And the answer is yes, but it's hard to relate to something about the string. So let's talk about this one first. So what is the high energy behavior? Clearly, it's small r. So this was high energies in r, so the length is the string is very long, and now I start taking r smaller, and when r is going to 0, I should be able to compute things like asymptotic freedom should kick in. I should be able to compute things in perturbation theory. But you see that there's this thing that I drew over here that happens, which is that the ground state energy hits 0 and then shoots in the complex plane. So it becomes tachyonic. The string ground state becomes tachyonic. You can think of this as a Hagedorn radius. It's a winding tachyon that becomes it's a winding tachyon that emerges when the radius is small enough. But from the picture of QCD, this is just the deconfinement transition. So we go back to this picture, you rotate your head, think of this as temperature, and we started with R long enough, so that means that we were at low temperatures, and you start increasing your temperature. Now you see that you hit, at some point, a critical temperature, which is the deconfinement temperature, and the theory deconfines. So my theory will no longer be composed of strings. Instead, it'll go back to some like quark Coulomb plasma or something like that. That's exactly what happens here. And then yes, indeed, when I take the radius to be very small, I can make computations that, like the partition function and so on with that Lagrangian, but that teaches me nothing about the string because I exited the confining phase, and I can no longer say that I have this string theory and try to compute things for that string. So this is not the best observable to do the job because there's a phase transition. So you can go and ask, will I be able to do it here? And here things are slightly better in the following sense. So I have a very long string. Now I have my Goldstone, and what is high energy? So of course, like if asymptotic freedom is to tell me something, it'll have to be high energy. So that means when these guys are highly boosted against each other. And then when they're highly boosted, there's this guy coming in, this guy coming here, and then there's expectations that this part over here of scattering, so that you can probably, so these are expectations by Dubovsky, that you can probably approximate this guy as a glue on attached to your string that's coming in and so on. So this part over here, there's expectations that maybe it's controlled by UV in some sense, but it's always in the presence of a very long string, which is a very IR object. So it's very hard. So there's maybe some qualitative expectations you can obtain by some approximations here, but it's very hard to use this observable to compute to control this observable in some regime from asymptotic freedom. Okay, so this is
Why should this process describe the by string action? Why should what happens?
because I have a string in isolation. I'm a large N, so I'm always working on
But now you're looking at some regime where the string has some very small but highly curved structure on it, right? This is
yeah. So I mean,
that's when those two guys meet each other at very high energy, in the sense that you're making some wiggles that has very high. So why should that process described by the string EFT?
no. Of course, yeah. I've moved on from the string EFT. I've moved on. So I have this gadget, whatever this is, which is the putative dual, again, the putative string theory, the full string theory, string worldsheet theory that describes Yang-Mills. Okay, this has high energies and low energies. And I told you that so far, people only know about these low energies, and low energies have these things, and it describes these two guys at low energies. Now I'm asking, can we go beyond this? So I'm forgetting about this, and I want to probe directly the high energies of this guy. I want to probe the high energies of this guy by using asymptotic freedom of this guy. And I'm describing two things that you may try that don't work on the nodes. This guy because there's a phase transition outside the confining phase. This guy because you cannot really do a UV computation because you're always in the presence of a very long string. So you cannot really decouple one and the other.
So the question, does that action in quotes exist or make sense at arbitrarily high energies? That's not obvious.
It's an assumption. So this is
why should it be two-dimensional, for example?
Yeah, you would think that the dynamics would go back to being described by the 4D UV action.
Well, what would you say about yeah, I mean, so this is the key assumption. We're assuming that there is a string dual to it, and it's similar to what you would say like in N equals 4 type 2 duality. So like the SCFT picture where you have like H theory, you can recast in terms of a string theory. And in that case, they have additional directions and so on. But that's strongly. It's always string theory.
I mean, you would expect it to be a strongly coupled string.
A strongly coupled string. You mean like the
couple gauge theory up in the UV? And normally, you would expect the string description to be bad at that point.
Yeah.
I mean, that's sort of the intuition from.
No, but it's still at large N. So like I'm taking my large N theory on one side, and then there's just the string coupling is small, but then like there's a tough coupling that's different, right?
I mean, in the n equal 4 case, the alpha prime corrections are big.
Yeah, that's right.
No, sorry, the curvatures are big. It's not. Yeah, okay. You say there's still a weakly coupled parameter.
Yeah, the string is still small. Yeah.
Where does the CDD factor? Which should be the description of the S matrix at sufficiently low energies.
Well, which one? Sorry.
The CDD factor that comes from the leading term, the non-Goldstone term, roughly.
Yes. So if I understand what you're telling me,
you're above those energies here, right? You're in the asymptotically free regime. You wouldn't see that, right?
You wouldn't see that. No. So these are low energy starts with this magnitude of freedom. It's e to the I, S over LS squared. So this is like the one that you would just get, like that's just the what you would get in, like, for example, like vertical string, the full S matrix is just this at all energy, but here you have corrections. So it comes with gamma 3 S cubed, also that dot. And then this is only at low energies, at high energies we don't know. And then the expectation you would get from here, well, like Dubovsky's expectation is that it goes again to something like this, but with a different coefficient, which is controlled by J. Yang-Mills. But it's no longer, a crucial distinction is that it stops being integrable. So it actually, like, it shoots these two guys, and then it will shower off into a lot of modes. Whereas at low energies, these guys, the two guys just reflect back and so on. So it becomes quite complicated in the UV, precisely because of the presence of this thing showers into a lot of submodes. Yeah. So it definitely is an assumption. We're assuming that this thing exists, and we want to learn something about this UV here. Okay. More questions? Okay. So if not, I'll jump straight ahead to the observable that actually does the job. There's nothing weird. It's actually precisely the same object that people use in lattice simulations to extract these ground state energies. And it's the correlator of two polyacoupled loops. So I'm still in R B minus 1 times S1, with radius R. And I'm going to keep R above the confinement transition. So R is above 1 over TB, so above this point. So I'm still in the confining phase. And now what I do is I wrap two Wilson lines around. So now I've rotated my head. Now this is the compact direction. And now I wrap two Wilson lines around this this compact directions, this fundamental Wilson line. Here I have an anti-fundamental one. Okay, and I put them so they have radius r. They're non-contractible, so that's why they're called Polyakov loops. I may use Wilson and Polyakov loops interchangeably, but they're always non-contractible Wilson loops. The ones I'm describing, and then they're separated by some separation tau, something of Euclidean time going in that direction. I call it tau and r. So okay, what's the picture? The picture is that this guy now, so this from a time slice here and time going that way. This guy is just a quark and an anti-quark, and they source a string in between, and this is just the thermal trace. I have the full cylinder here. I'm at large n, so the only topology is that of a cylinder. There's no higher topologies or anything. Or the other picture is one where this guy acted on the vacuum, created a closed string that's moving, and then it's absorbed at the other boundary. Okay, so this thing from the worldsheet perspective is the cylinder partition function, depends on tau and r. Importantly, this is not a CFT. So in a CFT, you'd have tau over r, and then that's by notation, but you would call this tau CFT, the usual modular parameter in a CFT. But we don't have this. Instead, you have a partition function that depends on two dimensionless ratios, which is tau over Ls and r over Ls. Okay, so many things still apply. You still have two quantization pictures, but they're not related by a modular transformation from one to the other. So what are these two channels? I'll write them explicitly. You have the open string channel. So Hilbert's trace over the Hilbert space of open strings, the one over here, and you do the thermal trace. So e to the minus r h off. And then here you have the other picture, which is the Wilson line creates a boundary state for your string, and you evolve it e to the minus tau h closed, and then you absorb it in the other Wilson line. And the two are equivalent. Like the two are the same, it's just two different quantizations for this process. Okay. And now the assumption will be, so there's this object, just a correlator, a two-point function of Polyakov loops in pure young meals. And this must be equated by, so that's like the duality statement, equated to the cylinder partition function of my putative theory. Okay. So now, good. Now let me see if I'm not missing anything I want to say. That's good. Yeah. Any questions?
You have not yet told us anything about open strings, right?
No. What do you want to know about the open strings?
Well, I just mean that we don't yet know how to formulate the worldsheet action for them. We don't know what degrees of freedom are at the endpoints.
Okay, so let me spend some time on that. Thank you for the question. Do I need this anymore? No, not need. Actually, look. So good. So I only described closed strings because in general those are the ones that have been most studied. But you can do the same thing for open strings. Same thing. I mean, we can go back to low energies, and I'll tell you what people know about this string. Yeah, for open strings. Open strings about this theory. So at low energies, you again have an effective. So the effective action is the 2D. So the worldsheet, whatever 2D worldsheet effective action, which is the one that we had. I just raised, and then you have a 1D boundary effective string theory. So what is this action over here? You can write again. So what does it look like? At low energies, it's just a Dirichlet boundary condition because you're telling your string to stop there. That's where you have the Wilson line. But then you only reach that at very low energies. You can have like this boundary condition. You can have some dynamics, which will be the dynamics of the Goldstone modes, so the various ripples of the string coming in and interacting with the boundary. So you have your boundary, that's your Wilson line, and then there might be some non-trivial dynamics encoded on the boundary. So you can do this by writing an effective string action. So this thing, okay, because I want to put it in quality here, but anyway, this thing is equal to, then you just write d, some one dimension, and then it has some cosmological constant. You can think of it as a mass, but it's not a mass for a dynamical, it's just some 1D cosmological constant. And then you can write various things, and these have also been classified. They need to be compatible with Poincare invariance, and Haroni has a very nice paper where he classifies the first corrections. The first one's called D2. It's again another Wilson coefficient, and it looks like this. There's this D0x, D1x squared. So the idea is that at low energies, you still only have the Goldstones, and you only need to tell me how the Goldstones talk to the boundary. And this is done by adding, so if I don't have this, I just have theories of boundary conditions for my Goldstones, but now I have corrections on top of that which describe dynamics and not trivial dynamics of the Goldstone touching the boundary. It could be that at high energies there's additional guys living here, but that's again, we don't know because we've integrated those out when we have this picture. Does that satisfy you?
Should we expect any Chan-Payton factors or anything like that?
So I don't think they're relevant when you have non-dynamical quarks, because I could dress this Wilson. Let me think.
But at some high energies, we're supposed to be able to describe the scattering of actual gluons.
Yes.
And according to you, we're supposed to be able to do that with this worldsheet.
Correct. So, I mean, I'm in. There's no dynamical quark, so my boundaries are not really like I won't have actual meson, and that's when you want the Chan-Payton factors, right? Because you'll have like your ion with plus, minus, or 0, and so on, depending on what combination of Chan-Payton factors.
How would you make something that carries the charges of an adjoint?
Yeah. So you take. So this is just a representation, right? So I choose this guy has some representation here. And then I need to put the two guys. If I take like fundamental, the fundamental will be in the singlet in general. But I mean, I think you could engineer by putting two, all the control you have is this guy over here.
But I thought that would mean that you would need the Chan-Payton factors.
No, okay, we're just I'm confusing flavor and color. So this is singlet. It's always going to be a singlet under color. Now the question is whether you can add an additional representation under flavor, some SUN flavor. I imagine you can. So you have to consider a collection of these, and then each of them will have you'll have a collection of them, and then each of them will have its own EFT description. I admittedly haven't thought too much about how to add flavor, but I don't think. I just don't.
Well, I guess I was actually talking about color, but you're saying that you never see anything like a weakly coupled gluon. Because you by fiat put in that the strings are all color singlets.
Correct.
Even though at high energies we expect that the kind of weakly coupled effective degrees of freedom are gluons.
Yeah, but my way of thinking of it is that this only applies literally on the confining phase. So as soon as you go to the other phase, like it should not be described by this. As far in the usual string perturbation sense, I don't know if you condense your tachyons and then things I can't comment. Okay, so good. So this is we need the low energies of the boundary. But now going back to this, these are just the answer to your question. Like, what are these boundaries for this theory? It's just some other boundary condition that could be highly complicated. Okay, so good. We're going to learn some things about these boundaries. That's the main point. Well, we'll see if we'll learn anything about these boundaries. Okay, so quickly, what is the point now? So this is a different observable that we can compute in effective string theory when these are very long. But now the whole point is that now I can dial tau and take tau as small as I want, and then asymptotic freedom will kick in, and I'll be able to compute this perturbatively. And then this is still something that will be in the confining phase. So the critical statement you should take away is that there is no phase transition as I take tau to be very small. So the reason is because these are just probes. I'm not compactifying. This is not a slab of my theory. I'm taking like something drastic in the theory. These are just probes of my theory, and I'm taking them close together. Okay, and when I take them close together, I'm just probing the high energies of the theory, the low energies of the theory, but I don't actually step on a different phase. And you can see this by going the same plot that I erased. You can do for the open string ground state energy. So this will be energy of the open string ground state as a function of tau. This is the open string, and then at high energies, again, it's linear. Energy is proportional to 1 over Ls squared times tau plus, and then there could be this mass here, which is 2m, which is some shift. And then it starts deviating. This is very similar to what we had before, but actually this is very bad because it actually goes all the way down here, and it's smoothly joins. So what we have here, we have a linear potential here, and what we have here, we have actually, and I'll explain why, we have a Coulomb potential. So this is the plot Coulomb. This is the plot of the quark anti-quark potential in Pure-Yang-Mills, and it goes from linear to Coulombic with no phase transitions. Okay, so this becomes negative, but it does not become tachyonic, which is very different from what happened here that I erased. At some finite temperature, I had a deconfinement transition. Here, there's no phase transition as you go from one phase to the other. So what is this diagram about? You can see it from here. I take the limit where tau goes to 0. And now what I have are two Wilson lines very close together, okay? And now I can zoom in and do this computation perturbatively. So what's happening is that you have your Wilson line and anti-Wilson line, and what they do is they exchange a gluon between one and the other. And then there's a whole series of diagrams where they start exchanging them, and then they all resum into e to the minus r. So r is as you go around. So it's the extensive factor. It's just proportional to the volume because you weight this translation symmetry in that direction, you get the volume factor times this diagram over here of a single one. Now you could consider more complicated diagrams where this thing does this, and then the same thing happens. They exponentiate and it appears here. These are the so-called webs, and they're one understood with derivative QCD, and they go on and go on. Okay, so the answer is that what you got is the short distances is the exponential of this connected diagrams from one another. Okay, at small tau, the leading one is this guy over here, because these coefficients, each of them comes with powers of G Young Mills, and G Young Mills runs with the energy scale. So these guys are suppressed as tau goes to 0, and the leading singularity comes from this guy. Now, as you know, when you just have a single gluon exchange and you do the Fourier transform to go to the position space, this thing is nothing but the Coulomb potential. So it's become in equals 4. This becomes 1 over tau, and once you take into account the running, it's 1 over tau log of tau, actually, with some coefficients, and in equals 3, it would be 1 over tau to the 0, and it's actually just a log of tau with some coefficient. The coefficient here is precisely the tube coupling, which has some dimensions in 3D, and the coefficient here is just beta 0. So like when you're doing actually, I could write it, it's just it's the number, it's the one loop beta function of the running of the Young-Mills coupling. Okay, so the statement is that when you take the two guys to be very close together, this partition function, so this is z of tau r goes to as tau goes to 0. So this partition function that I had over here goes to this thing, and now you see that it's produced a large r. It produces so this is true at small tau for finite r, and then you can just compare, and this will give you the Coulomb potential that people see on the lattice over here. Okay, so maybe this was too quick. I'm happy to give clarifying questions or give you more details offline. But the basic point is it took 1 hour, right? So I have like 5 minutes.
You've had a lot of questions.
Okay, yeah, good. So yeah, let me know when I should stop. But good. So at small tau we have this thing, and now we go back to this equation, and we have a string observable because I hope I've convinced you that we don't change. There's no phase transition anywhere, and you see the same thing in holographic models. We change tau, and we keep r above. So I never play with r, and I'm keeping it above the confinement temperature. So I am in the confining phase, and now there's a regime where this thing is controlled by a perturbative computation, which I just know I can compute and obtain. Okay, so now I want to match the two and see what this thing. That limit teaches me about distributive theory and its boundaries. Okay, and so this is what we call the imprints of asymptotic freedom on these confining strings. I'll discuss two main things. The one will be about the closed string spectrum, and the other will be about the dynamics on the actual string worldsheet and its boundaries. Okay, so good. Is there any more? Good. So the spectrum. So I want you to take a look at this formula over here, and we're going to rewrite it. Yeah, this was bad. I guess. Okay. So there's that formula over there for the partition function in terms of closed string states. I'm going to insert a complete basis of states, and I have the Z cylinder. I'll stop writing cylinder. Tau and r is equal to. And then here I have sum over the various string states of the Wilson line coupled to the state up to the value squared, and then e to the minus tau energy of this guy. And now I'm going to write this as some integral over some density, rho sub w, because it depends on that boundary, the Wilson line. That depends on the energy and the radius, and has e to the minus tau energy. Okay? And this thing here is just to be explicit, it's this coupling. W and square times you just measure energy minus temperature. Okay. I've just written it as a Laplace transform of some density. There's just a spectral density of states weighted by this thing. And then now the statement is that I know this partition function at small tau. Now I come here and ask, okay, I have this Laplace transform, and there's the usual logic about Laplace transforms. When tau is small, this means that this integral is dominated by the high energies of this spectral density. So now I can go and do a Cardi trick in a sense. This is how you would obtain the asymptotic density, like Cardi formula for the asymptotic density of states into these CFTs. But instead of using modular invariance and the central charge and so on, I just use asymptotic freedom, like that result. So what I'm doing is I do an inverse Laplace transform to this, and that extracts rho W, V of R, and then I do the inverse Laplace transform on that result with these two things, and I obtain the asymptotic density of states for the asymptotic spectral density. There's one subtlety that I won't get into here, which is the distinction between the energy and the mass of the string. So really what I'm doing is looking at the mass of the string, because the statement is that from the 2D point of view, if your string is moving and has some some kinematic energy in some direction, that also contributes to this spectral density. But then all you need to do is that instead of taking an inverse Laplace transform, you do a small modification where you also do a Fourier transform in the transverse momenta, and then you extract the density of mass, so the mass density of the strings. This is not supposed to make much sense. It's just if you watch the recording once the paper comes out, you'll say, "Oh, he lied to us." I just simplified it for the purpose of the talk. You should think of it as an inverse Laplace transform, just souped up, so that you get the actual spectrum of like the masses of the string, and it's not contaminated by the kinetic energy of the mode moving in space. Okay, I'm happy to give more details afterward. So good. So what do we get for this asymptotic density? I won't walk through the inverse Laplace transforms. I'll just jump ahead to the result. And we find that in d equals to 3, we can do this for both, equal to 3 and equal to 4. I find that in d equals to 3, this thing goes like mass to lambda, which is the tooth coupling, that's r divided by 4 pi minus 2 plus dot dot dot. There's corrections. And then in 4 and d equals to 4, I find the exponential of square root. This number comes from the beta function, 24 pi over 11, just some number, radius, the mass, divided by log a square root. Okay, so we obtained the asymptotic spectral densities of these guys just from asymptotic frequency. Okay, and now what you can do is, okay, so you can compare this to what you would expect, which is a Hagedorn growth for these string states, right? So if I don't weight my spectral density by the coupling to the Wilson line, and I just count the actual multiplicities of these guys, what I usually expect in string theories is that the spectral density grow like Hagedorn. So what's the Hagedorn growth? Is rho of h, the function of mu, is e to the mu divided by some t Hagedorn. Okay? So some exponential growth, which is linear here. You see here we have a milder growth, which is the square root of mu, and the interpretation, the way you should interpret this is that this factor over here is damping the growth that you would get just from the multiplicities of your states. Now we don't know like the Hagedorn temperature from this picture. I haven't convinced you of that, but it's just if we have like what we would expect is such a growth, which is what we would expect when we compute the truth partition function, which would have some issues. By the time you add some boundaries and has this thing, it should become much milder and go to these two guys. So what is this telling you? It's telling you that this coupling here needs to decay exponentially with the Hagedorn growth and cancel that, and then be left, leave you with this. So what we learn is that this coupling, if you have a Hagedorn growth, should go like at least e to the minus mu over th, and then times whatever you need to be left with this. And so it's telling us that the closed strings coupled to Wilson line, so high energy closed strings couple much weaker and weaker to the Wilson line, in particular exponentially weaker, to damn that. And the way you see this is that, so the reason why this has to be the case is because there's no phase transition as I move tau. So if tau becomes small enough and you have such a growth, then at some point this will overwhelm and trigger a phase transition. But now this is damped by the coupling to the Wilson line, and I find a finite result all the way, I mean, as it goes exactly to 0, there is one divergence, but I don't find any divergence at finite temperature, a finite tau. Okay? So this is one of the main results, which is that we learned that the coupling of high energy string states to the boundary must decay. We still don't know what the boundary is, we still don't know what the full theory is, but whatever, if anyone comes to you and says, I have found the string dual to Young Mills, it better satisfy this. Okay, and now I'll just finish by discussing a bit quicker. The other imprint that we found with asymptotic freedom, which is directly on the string dynamics. So you would like to zoom onto the worldsheet. I'd like to see where could such a thing come from? What does it mean for the worldsheet of my string to have such a decay? Okay, and for that, what we're going to do is jump onto the worldsheet and describe instead of in terms of an action, in terms of scattering data. So we have an S matrix that should capture, so as S goes to infinity, should capture the dynamics of this guy. And then we have this thing over here that I already drew for you, which is a Goldstone coming at some momentum P against the boundary and then shooting off, which is what's known as the R matrix, P. So it's a reflection matrix for a Goldstone against your boundary. Then the statement is that this function at high energy, of course, there's many more, right? There's 2 Goldstone, 3 Goldstone, and so on. But there's one observable, and it's the coupling of a Goldstone to reflect against the boundary. And so the statement is that these two guys, the S matrix and the R matrix, are proxies for the action over here. So learning about those two guys will teach me about the dynamics that are described by this logarithm. If anything, like it's just the usual statement that matrices capture dynamics in a way that's the redefinition there and blah blah blah. Okay, so the statement what I'm trying to motivate is that we'll try to see what consequences asymptotic freedom has, namely this thing that I'm just erasing, this same limit for this function. What consequences this has for the R matrix and then the S matrix. Now this becomes very difficult because it requires that you can connect finite volume physics to scattering data. Why? Because Z tau of R is necessarily the finite, and studying as tau goes to 0, so I'm very much a finite volume, and I want to relate it to scattering objects, which happen, scattering data, which happens strictly when the string is very long, right? And I have like something happening on a very long Hilbert space. We need to connect these two things, and in general, it's very hard to connect them. So what we do is we take a toy model, and I don't want you to believe that, so it's a toy model. I don't want you to believe that you should, I don't want you to take this as the truth. It's just a toy model to see what we can learn, and we're going to assume integrability. So integrability is a very strong assumption. It's saying that there's no particle production. When I scatter these two guys, they just reflect and do their business, but they only they only acquire a phase. This is very much not the case, and in particular, we expect things like this. So when two things scatter, they shower into many things. It's very much not integrable. It has been measured that it's not integrable. But nevertheless, we take this as a toy model to see in a putative integrable theory, what would this thing, so remember the limit is different, so goes to 0, I got e to the minus r v coulomb. So what would this teach me for scattering data there? And then we'll see that the lesson is something that probably generalizes beyond integrability, and the question becomes, can you prove it or can you? And okay, so I'll speed up. Please feel free to leave if you have other commitments, or kick me out. So just one, so what does integrability buy you? It buys you some formulas that go under TPA, the name of TPA, which is thermodynamic Bethe-Ansatz, and I'll just quote the formulas, but they have a beautiful derivation by Zamologico. And the basic point is this, so that you have minus 1 over R log of Z, this same Z of tau and R, as R goes to infinity, with an infinite volume, is given by this thing, 1 over 2p, by an integral of dp and something, log 1 minus R matrix at IP squared e to the minus something called observable energy. And so the energy is some function that solves some equation, the so-called TBA equation, epsilon p equals 2p tau plus 1 over 2 pi integral of dp and something funny, that's 1 over I d prime as, bear with me, I'm writing the whole thing because every detail will be important. Log 1 minus R of like p squared e to the minus epsilon p. Okay, stop. So there's these two equations that compute for you the log of the partition function at finite tau to infinite R So this projection function here, in terms of something called the cellular energy over here, which is some function that in principle comes from this equation, but that's a complicated integral equation because it's on the left-hand side and here inside some interval. So that's hard, but you can put it in a computer and then iterate. And given the data of the S matrix and the R matrix, if somebody hands you this and they're integrable, then you can obtain finite volume physics, and namely this, the free energy, in terms of those two guys. Okay, I won't go through how this comes from, but it needs very crucially integrability. Okay, so what are the ingredients? The ingredient is the S matrix in this funny combination that I'll comment on in a second, and the R matrix. Why is it IP and not just P? Well, that's because we rotated our head. So if I look at this as a Lorentzian time flowing in this direction, I have a reflection process, and that's R of P. If I look at it with time going this direction, I need to do a double weak rotation, and then this becomes R of IP, which is the process for the boundary to emit two Goldstones into the bulk. Okay, and then the fact that they're related is basically crossing for this R matrix, and that's what appears here. So each boundary is shooting particles in pairs of two into the bulk, and then each of these pays a price of R of P. And that's the way it appears here. Okay, and then they go on, and the interactions in the kernel depends on this in this way. Okay, so now, so what do we do? Well, the first thing is to notice that this object over here is nothing but something called the time delay, the Wigner time delay. Okay, so it's a two to two process. I have a particle going in. You should interpret this as this trajectory, xi going in this direction, and then I have a particle coming in. So yeah, one goes that direction, the one comes here, and then it comes out. So these are massless particles. They go in the light cone, but it comes out with some delay if it's fast. And this time delay is precisely given by this. But now, if I have massless relativistic scattering, this actually has to be by causality greater than non-negative. Okay, I can only have time delay, no time advance. There's been a lot of debate whether this is actually true or only true up to the uncertainty principle, because you should really think of it as wave packets. And then to talk about a particle trajectory, you need to make sure that you can measure things and so on. So some people were proposing that it can become negative up to something that depends on the scale and so on. But in the paper, we show that just from analyticity, unitarity, and crossing of the S matrix, this follows. So this is strictly positive or strictly non-negative for any energy. Okay. So the point is that whatever your S matrix is, you don't need to tell me. Whatever it is, it will be positive, and that immediately implies a bound because this thing is always negative. If you don't have this transition, this thing is negative. This means that the pseudo energy must be bigger than 2p. Okay. So this is the first result, which is an integral theory. If you have massless elastic scattering, interactions can only lower the energy. So this is the energy that two particles would have in a free theory. So energy times time. So this is a Boltzmann factor that the two particles would have in the free theory. And now if you add interactions, they can only lower this energy. Okay, so causality is telling you something about the interactions of this. Do I mean smaller? This is small. I mean smaller. Thank you. So this is negative. Yeah, clearly. This is a Blackboard effect. The closer you are, the less things. So you drop your ability to reason or not. So good. So interactions can only lower the energy with respect to the free theory. Thank you. Okay, so now you just move through. You now use this thing here. You put it over here, and you massage the log and so on, and then you find that this thing, 1 over r log z tau r, is smaller. It is equal to 1 over 2 pi integral of dp r over p squared e to the minus 2p. Okay, and this is one of the other formulas, which is a bound in the free energy of whatever theory you have in terms of scattering data. And this is what we call a causality bound in thermodynamics, because this is a thermodynamic quantity, and the only input was causality of for the interactions. And why am I saying any of this? Is because, well, now we've been able to relate the partition function to scattering data, in particular the R matrix. And now we can go and use this result and say, okay, now I go back, and I'm assuming that I have this toy model, this toy string, which is integrable, and it has to reproduce a confining behavior, the asymptotic free behavior over here. I plug the Coulomb potential that I raised over there, and then we see that there's an upper bound on the R matrix to reproduce that behavior. So this we worked out in d equals 3. So Because in any case, it's a toy model, so I'll just give you an answer. And it's that the R matrix in this channel, the one for emitting two particles into the bulk, has to be bounded by square, the Tooth coupling divided by flux. Yeah. So yeah, so this I'm getting to the concluding points. The whole point is that if you have a theory that has its interaction and so on, the emission, the probability for emitting two particles from the boundary, so two Goldstones from the boundary at high energies must decay as 1/p. And this is not something that comes from unitarity or anything. This is a condition that comes only from asymptotic freedom. Now, this is what would explain the asymptotic exponential decay over here, because a high energy state is composed by many excited Goldstones and maybe other excited particles. And then such a decay of the R matrix is what, it's basically it's basically telling you that a high energy string will decouple very weakly to the Wilson line. And of course, this was only in the integrable setting, and we expect that something similar will work, where you use positivity of time delays to say that energies have to always be lower. We expect that to continue to be true beyond integrability. And then if you can massage that into bounds on thermodynamics in terms of our matrices, we expect that you will probably show, like, the precise form will be different probably, but we expect that these R matrices will also decay. So yeah, that's basically it. Just want to, the takeaways is that we can learn something of this putative string dual to Yang-Mills from asymptotic freedom. And yeah, the main takeaway that we've learned from this is that Wilson lines couple very weakly to excited strings. And with that, thank you for your attention. Only half the room left.
What about the interpreting the cylinder partition function as a trace over the open string Hilbert space? What do you learn about the density of states?
So there, it doesn't control so much the density of space, because it's not it's not small r. So if I had small r, then I would learn about the asymptotic density of the space.
Because it's not conformal.
That's right. Yeah. And if anything, like I could take
But what do you learn? What can you?
Right. So something you can learn is you can focus, for example, at r. So what I told you was a finite r. So r. So I told you now going to 0 r finite. Well, not finite, at fixed above the confining temperature. But now I can take in particular r goes to infinity. And then what do you learn? So you have in this, I guess I'm not a trace anymore, but you have trace of e to the minus r h up. So in this limit, you see that I clearly will only be left with the ground state. So as r goes to infinity, I will only be left with the ground state. It will be e to the minus r of energy of the ground state. So what we learn is precisely this fact, that the ground state energy as tau goes to 0 has to be Coulombic, which was already known. But that's why it's from this perspective, it's not so interesting. Now you try to ask, what do you learn at finite at fixed r?
Well, what happens if you try to compute that using the Nambu-Goto action?
Oh, it failed miserably. So if you just take Nambu-Goto gives you this, and then you can so Nambu-Goto gives you some result that does this, and it hits the open string tachyon. So when you're doing like a bosonic string, even if it's a critical dimension, there is some Casimir energy, which is with the wrong sign, such that at some finite tau, you actually obtain a tachyon. So it really failed. And other things would need to come in to produce this Coulomb behavior.
Even though r has gone to infinity.
Yeah. So r going to infinity just restricts it to the ground state here. If r is finite, then you need to take into account other guys. So like e to the minus r, connect one, e1 tau, and so on.
The ground state is not, sorry, I'm just getting confused. The ground state is not being accurately captured by the Nambu-Goto action.
Right. So where does So where does the effective string theory hold? It holds when tau and r go to infinity. Both of them need to go to infinity. And so I see your point. Your point is I'm taking r to infinity, so I'm in the low energy theory. I've already why can't I use the effective string action, which would be just Nambu-Goto? The answer is because you're still taking that only holds for long strings, and you're looking at a short. So when tau goes to 0 here, you have picture is this one separated by distance tau. So yes, I'm looking at the ground state that's necessarily low energies, but it's not enough low energies if tau becomes smaller than ls. And then my string my effective string theory no longer holds. So that is extremely limited. It only holds for low-lying states of very long strings. And so that's
If there are no more questions,
Is there any conceptual argument for the existence of that worldsheet axiom?